You know, we've always taken it for granted that our intelligence, our creativity, everything that makes us us, comes from having a special brain. But what does that really mean? What makes it so special? Today, we're going to peel back the layers of our own evolution to find out what truly sets the human brain apart. So let's get right into it. So let's just start with the biggest question right out of the gate. What is it about this 3-pound chunk of tissue that lets us do everything from writing poetry to exploring other planets? Now, the common wisdom, the thing you always hear, is that it's all about size. But as you're about to see, that simple story, well, it's just not true. All right, part one. Let's just go ahead and tackle that big, pervasive myth head on. Is our brain's incredible power really just a simple case of being the biggest one on the block? Yeah, this is where that whole bigger is better theory completely falls apart. Our brain weighs in at about 1,400 grams. An elephant's brain? It's a massive 5,000 grams, more than 3 times bigger than ours. I mean, if sheer size was the only thing that mattered, elephants would be running the world, right? So clearly, there's something much more subtle and interesting going on. And that brings us to the real secret, the first major clue in this whole story. It's not about how big the house is, it's about how many people you can fit inside. The real magic isn't size, it's efficiency. It's all about how many neurons, the brain's processors, are packed into the space you have. So if our brain isn't some totally unique, magical design, then what is it? Well, the evidence points to something fascinating. Our brain's biggest advantage comes from its construction plan. At its core, it's a primate brain, but one that's been scaled up following a very, very economical set of rules. Okay, so check this out, because this is the key difference. For most mammals, like rodents, when the brain gets bigger, the individual neurons also get bigger and puffier. That means they take up more space, they become less dense, and you quickly hit a wall. You just can't fit that many more in. But primate brains, they follow a different, much smarter rule. As our brains get bigger, the neurons stay the same small, compact size. And that allows for this incredible density, just packing more and more processing power in. And I mean, look at the numbers. They really tell the story. That huge 5,000-gram elephant brain, it has about 11 billion neurons in its cortex. Now look at us. Our brain is way smaller, but we've crammed in a whopping 16 billion cortical neurons. That's 5 billion more processors in a much smaller, more efficient package. That is the primate advantage in a nutshell. The neuroscientist Dr. Susanna Herculano-Hausel, who did so much of this groundbreaking work, she put it perfectly. We don't have some sort of magical from-scratch design. What we have is a primate brain that was simply allowed to keep growing along these incredibly efficient linear scaling rules. And the result was an explosion in neuron count. Okay, so what is it that allows for this remarkable primate efficiency? To understand that, we have to zoom in. We've got to go from looking at the whole brain down to the microscopic level of our genes and the amazing developmental programs they run. A really central idea here is something called the radial unit hypothesis. Now that sounds complicated, but just think of it as the basic construction manual for building a cortex. It all boils down to how our very first brain cells, these things called progenitor cells, decide to divide. And those early decisions shape literally everything that follows. I love this analogy. Think of it like building a city in 2 main phases. First, in phase 1, the cells just clone themselves over and over. They're laying down the map, making the city grid bigger and bigger. Then they switch gears. In phase 2, they start making neurons. This is like building the skyscrapers on that grid, making the city taller, denser, and more complex. And the crazy thing is, tiny little tweaks in how long you spend in phase 1 versus phase 2 can result in a massively different brain. And what's pulling the strings on all this development? Well, it seems to be small but powerful updates to our genetic software. Scientists have pinpointed some really key changes. For instance, gene families like DUF12-2020, which are super important for neurons, just exploded in number in our lineage. We also got a new, souped-up version of a protein called GLUD2, which helps our high-demand brain recycle key chemicals more efficiently. And of course, there's the famous FOXP2 gene, tied to language, which shows all the signs of being fine-tuned by evolution. So we've got this incredibly dense, efficiently built piece of hardware. But hardware is only half the story, right? How is it all wired up? How did we develop the software, the complex behaviors like language and tool use that really define us? Well, it turns out the brain's wiring diagram is an absolute masterpiece of network design. It's what engineers call a small world network. The best way to think about it is like a perfect city. You've got these dense, tight-knit local neighborhoods where information can be processed really well. But you've also got this incredibly efficient subway system of long-range connections or shortcuts that let you get from any one neighborhood to any other super fast. It's the best of both worlds, amazing local power and lightning-fast global communication. And how did our amazing abilities, like complex tool use and language, arise from this network? Well, one really powerful idea is the co-evolution hypothesis. And here's where it gets wild. When you put people in a brain scanner, you find that the structured actions of making a tool and the structured syntax of language, they light up the exact same parts of the brain, including the famous Broca's area.
And the implication there is just stunning. It suggests that the neural circuits our ancestors developed for planning out the sequence of actions to make a stone tool, hit this rock, then that one, then shape this edge, that very same mental scaffolding may have been hijacked or co-opted by evolution to build the sequence of grammar and syntax and language. Our ability to build complex sentences might have literally grown out of our ability to build complex tools.
So, after all this, what's the one big secret to the human brain? Well, the big reveal is there isn't one. There's no single magic bullet. The real answer is something called mosaic evolution. It's a whole collection of things. These efficient primate scaling rules, a few key genetic tweaks, some unique developmental timing, and the incredible coevolution of skills like tool use and language, all building on top of each other over millions of years. It's an incredible story, a true evolutionary triumph. But let's be real. Building and running a genuine supercomputer inside your skull, that can't be cheap, right? It doesn't come for free. So is there a price we pay for all this extraordinary complexity? And that brings us to our final, crucial section, the price we pay. Because in evolution, everything is a trade-off. There are always costs and benefits, and our amazing brain is absolutely no exception. And here's a really profound trade-off. If you want to predict how long a species lives, what's the single best factor to look at? It's not their body size or their metabolism. It's the number of neurons they have in their cortex. In fact, that one number explains an incredible 74% of the difference in lifespan across all sorts of animals. The bottom line? A complex brain needs a long life to grow and to learn. Our intelligence is paid for with a slow life history.
For maybe the most powerful and personal example of this biological price, we have to look at the maternal brain. The changes a mother's brain goes through during pregnancy are just staggering, and they really put the immense cost of creating another complex human being into sharp focus. I mean, to build a new human, the maternal brain essentially rewires itself. The pituitary gland literally gets bigger to pump out the necessary hormones. The brain rewrites its own rules, making itself resistant to insulin just to make sure enough precious glucose gets to the developing fetus. This biological stress is so intense that it can make some existing conditions worse and, as we know, can increase the risk for postpartum mood disorders. It is a very, very real physiological price to pay. And finally, of course, there's the sheer energy cost. It's an absolutely mind-boggling statistic. Our brain is just 2% of our body's weight, but even when you're just sitting there, doing nothing, it's chugging down 20% of your body's total energy. 20%! Running this biological supercomputer is incredibly expensive. So the story of the human brain, it's not about a single miracle. It's this beautiful, messy, brilliant mosaic. It's a primate brain, scaled up with unbelievable efficiency, fine-tuned by a handful of genetic updates, and wired for incredible collaboration. And it's all paid for with a slow life and a massive energy bill. Which, of course, leaves us with one final, incredible question to ponder. What's next? What will be the next chapter in our brain's evolution?